So there are several concepts. And one is hidable help. So means that in Rn B, where B is Euclidean metric, then some K is bounded, is compact if only if is bounded and closed. That's hidable help. So we have shown this direction in a general way. So it do not need to be RND. This direction is correct. Okay, that's last time. So how about this one? This one is a little bit tricky. So it seems like, okay, let's say maybe we have a R2 graph. We have a set that is bounded and closed. So thinking about like this. So it is bounded, so it can be covered with a square, a large square. Right? And we're trying to prove that it's compact. So let's say if there exists an infinite open cover that does not include a finite subcover, right? That it must be some the little block, the part in the little block that cannot be covered by finite open sets. So if this one can be covered by finite open sets, this one can be finite, this one can be finite. Combine them, you'll get a finite open cover. It's a one cool for you. But since we're saying that, okay, this one is not compact, so there must be something wrong. Alright. So let's say maybe this one is wrong. There's something strange happening in this block, that this one cannot be covered by finite open sets. It just like keep divided, and something gets wrong. Just keep dividing it. Keep dividing it. So keep doing this. Well, you'll get a point. You'll get a point that seems like if the point is in a block, then the block cannot be covered by finite open sets. But it must have some, there must be some point because this one's closed. Right. So there must be some limit point here that lies in the whole K. And by the definition of the open cover, it must be covered by some open set. That point itself must be covered. So let's say this one. It must cover by some open sets here. So for a little block, it must lies in this open set, which contradicts the process that we choose these blocks. That's the proof of hiding up. A little bit complicated. I remember I first see this one and I just like cannot understand it for maybe 3 days or 4 days. Let's try to feel that you're trying to find some point that must be covered by a finite open cover, or precisely by only one open set. and which contradicts the process that we find a point that we want that to be not covered by any finite open cover. Finite open subcover. Cool. So this one can be pushed into RD. So we subdivide this set into like 2 to the n blocks, hyper blocks, something like that. That's high level. And this one. Oh, not write it down, but just like feel it. If you need like concrete proof, I can do it. I think you have to show. You have like understanding when you're doing the video. Another important proposition is K is compact and then only if all infinite subsets of K. K contains, sorry, not K has a limit point. Sorry, S. Okay, S has a limit point. Okay. So that's why I want to teach sequence before topology. It's because that this proposition might seems hard to understand what we consider something like infinite subsets of a set. And you can think about it like we're trying to say that every sequence has a converging subsequence. It doesn't make the same thing. It's at least easier for me to understand what we.
That's but that's you.
Yeah, but what I mean is like, it's not easier to prove, but it's easier to understand what we care about these things. So we care about sequences, but I don't know what we care about infinite subsets. So let's prove it. I'll prove which side? Compact. Yeah, I'll do this side first. And this side is so complicated that I may not be able to finish it in like 10 or 15 minutes, so I'll omit it. And maybe if we have time, we can like talk about it later, or I just like record a video about this one. I will understand this one. So I'll only do this one. Let's say, so we're thinking about like, we're saying something is compact, then there exists a limit point. And again, we'd like to see what was going on here. What's the limit point? The point is if for any open set that contains that point, it contains infinite many points of S. Right? That's the definition of limit point. And so, what do we mean by okay? So if there's no limit point, which means that around every point there should be at most finite points of S. But we know K is compact, so we can choose finitely many open sets. So let's say S is an infinite subset that has no limit point. then for all P in K, there exists some UP where P belongs to it open. Such that UP contains at most one element in S. So we're thinking about like this one, it has no limit point. So you can always find, but for this point, you can find this open set here. For this point, you can find this open set. Like for this point, you can find this open set. For something, this point, you can find this open set. Alright, so you always can find an open set that contains at most one. If P belongs to S, then 1. Then if P does not belong to S, then 0. So you can find such open sets like this. And you know clearly this one contains P. For all, so this one contains all P and K. Alright. Is that open cover? Finite subcover. But if there exists finite subcover, then this finite subcover at most covers this many of the points in S. But we know that S is infinite. So it leads to contradiction. That's how this way goes. Cool. So we call it like sequentially compact. Every is equivalent to every sequence have a convergence of sequence. So like for this part, you first try to prove that if this one, then it can be covered by, there is a countable subcover, and then if you have countable subcover, then you can find a finite subcover with the countable subcover, something like that. And I'll record that video maybe like after 2 days, and you can check that. But I believe that the video have mentioned how to prove it. Next, connected. So this one is the final important topology notion. After open, close, compact, that's one is connectedness. So we're thinking about I think this is more about the set itself and not, as what I said, the functions or the sequence of it. So it describes more about the space itself. We're thinking about something like this, but not. This one's connected, and maybe this one's not. So we're thinking about some notion about this one. It's not. It's very intuitive why we consider something about connectedness.
Sorry, can you explain again what does it contradict to?
Okay, so if there is a finite subcover, let's say, I just keep destroying the shocks. P from in K, UP. UP prime, sorry. And we know that each UP prime, contains at most one element in S. So UP prime contains at most finite point in S. But this one covers K. So this one covers S. Finite points. There are several ways to define the connectedness. I think what you have encountered is there is no two sets that like non-empty with a closure is a closure intersects B equals to non-empty. The interval is empty set. So your I think your version is one. C is connected. No A, B, and both non-empty, such that yep, I think this one. I think over this one. We're doing this one.
This is not a routine definition.
This is a routine definition. No. Sorry. Then what's a routine definition? I forgot. There's like so many definitions about connected. Like maybe like there exists two, like open relative to non-empty set open relative to the original set. I just forgot what word we used.
The intersection of A and B closure is empty.
A and B closure is empty.
And also the B closure intersect A.
B closure intersect A is empty. Okay, I see. If no A, B, C. So how does the formula? If no what? If no A, B being C subset, which is not empty set, that satisfies this one. So how this looks like? Alright, the previous definition is wrong. I just remember that this, yeah, this one's more correct. Here's definition one, but I prefer. No, I'll just use this. Okay, I'll just use this. So in this case, you can find that this one's closure is empty with this closure intersects with this one is empty, and this closure intersects this one's empty. So this one's not connected.
I'm confused. You write A and B bar intersection and B bar and A interaction, so that's the same thing. That's why typos are so important.
But this one you cannot find like two sets that has this one, because like you say that something like A is somewhere here, then this one, the boundary of this A either lies in it should be lies on if some point of boundary lies in A, then it also lies in the closure of B because it's the boundary. Right. So because like this point is in both this one, B bar and A bar, and it must be contained in one of A and B. Sorry, I forgot. A equals to C. So it cannot be empty. Cool. Something maybe not like that proper, but an easy way to remember the like. Do you remember I've told you about like we use like K for compact and U for open, something like that. And a way to remember this maybe like closed, open, connected, compact. Combine them would be something like this. Okay, cool. Examples. I would like to write down example that, I mean, you maybe think about like connected means that there's a line that we can connect things. But that is not the case. This one is called path connected. If there exists a line. Right. Examples that is connected but not path connected is this one. We're considering in oscillator. And trying to, you have the y-axis and you have this one sine 1 over x. This one's y-axis. So consider this set. Okay. Consider this set. X sine 1 over x. Sine equals to 0. And y-axis 0, y. This one is connected. So you cannot separate them. But this one's not path connected because you cannot find a path from here to here. This one is not. It just goes for infinite. You will not attain this line. Because like if you attain some line, there should be some way that the limit is this point. I use the calculus notion. But you know that it just oxidates here. So when that converges to this point. So there is no path. Makes sense. I think the last one is Cantor set. Cantor set. How much time do I have?
It's 9:52.
Okay, I can finish Cantor set. Cantor set. So, like, Cantor set is a special set that we consider in analysis. So, like, when we study analysis, one of the main points is to study, like, the counter examples in analysis. And the Cantor set is one of the, like, the most classic counterexample. So it's so like maybe you're considering something like, is there a set blah 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 blah? So it's kind of satisfy that property or something like that. So Cantor says construction is like the first step is to bring a 0, 1 interval. Is the zero step, and the first step would be like just like rule out the middle part of the set, and then 0, 1 over 9, 2 over 9, 1 over 3, 3 over 2, 9 over 7, 9 over 8, 2, sorry, 1, 1. So you're just keeping like rule out the middle of 1/3 of the interval and take intersections. You have Cantor set. So it seems like it contains like pieces, but not a whole interval. But this one, like, if you write it in, do you remember we have talked about like binary representation. So this one can be in a, what's it called, binary, trinary. That's also the language, 三进位制. So you can write down this one as something like Cantor says equal to 0.8182 blah 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 blah. Or AI equals to 0 or 2 in 三进位制. So like 0 points, it will be 0.020002, maybe like something like that. It's just like which part are you in? So there will be 0.0 blah blah blah. This part will be 0.2 blah blah blah. This part, if the point is in this part, it will be 0.00 blah blah blah. This one will be 0.02, 0.20, 0.22. Anything looks like this, you make sure that it lies in like every layer of the Cantor set construction. So it lies in there. So you can describe it like that. So like by this representation, you can find one is like Cantor set is uncountable. Why is that uncountable? Because we're considering like an infinite sequence that consists of 0 and 2s. And I believe that if this consists of 0 and 1, you know why it's uncountable. Just like change 1 to 2. So it's still countable. Proposition 2 says closed. Why is it closed? A very like intuitive way to see this is because every step is closed, and we're taking intersection over these steps. So any intersection of closed set is closed. So this one's closed. Proposition 3, C contains no isolated points. Do you know what is isolated point? I forgot if you have this kind of thing, or say like every point is a limit point. It's like every point in C is a limit point. That's it. So isolated point is a point that is not a limit point. And why is that? Why is that? Like for point 0 point, that's A1, AN, blah blah blah, in C. For all r larger than 0, there exists an m such that 3 to the m, 1 to the 1 over 3 to the m is less than r. So if we can find infinitely many, or what, at least one point in, I forget what you use, D, right? So if we can find point and that's D 1 over 3 to the n 0.81 and blah blah blah. Besides the point itself. Then right? So we're considering this one C, and it kind of says like this, something like this. And we're saying that if you want to find a point in R, you can just search the little circle 1 over 3 to the n. If we can find point here, and we can find point here, so for all R larger than 0, we can find a point. So that this one is a limit point. Okay. Let's say if am plus 1, that is the m plus 1 decimal here. That's not decimal. The m plus 1 place number equals to 0, then consider 0.A1, A2, blah 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 blah. AM2 0, 0, 0, 0. If it equals to 2, consider 0.A1 blah blah AM 0. Sorry, no, that's good. I think that'll be fine. So we're constructing this something like 0, 0, 0, 0. So this point, the distance from this point to this point is at most here, right? Is at most here. So it is at most 1 over 3 to the n. Because that's what? We're considering 2 times. Considering like the distance between, let's say this one, 0.81 am 20000, 0.81 am 0, sorry, am plus 1, as that's all equal to, as that's all equal as to, so you know this one's 0, right? 0 something. At most 2 times m plus 1. This one is am plus 1. And the same for this one, it's just like same argument. Maybe you can try it, and maybe like 2 is better. 2, and there will be 1. Okay, like same argument. So yeah, contains no isolated points. Cool. So that will be like main proposition of the Cantor set. How much time we got?
It's 10:05.
It's 10:05. Okay, I think that'll be.